Assalamu alaikum everyone. I am Dua Sattar and today I am going to present my CEA presentation along with my group members Sana Naeem, Fatma Noor and Ali Hayasi. Our project is about building an electronic stethoscope with a preamplifier and filters. Normal stethoscopes just pass sound directly to your ears. Electronic stethoscopes are better. They boost the sounds first. In our project, we built a system that amplifies body sounds like heartbeats and breathing and then filters out unwanted noise. So, before building that circuit, we had two goals. First, to amplify weak heart and lung sounds using a preamplifier. Second, to add filters that let us select which sounds we want to hear. Heart sounds between 20 and 150 Hz and lung sounds between 100 and 1000 Hz. So, the problem is simple. Regular stethoscopes don't work well in noisy places. Doctors can miss important signs because the sound is unclear. We need a better system, one that boosts and filters body sounds clearly and is also cheap and easy to build.
Assalamualaikum. First, I will explain the components used in our circuit. The main component is IC741 operational amplifier. Its function is to amplify weak heart or lung signals. R1 and R3 resistors are used for gain determination, meaning they control amplification level. Capacitors C1 and C5 are used for input and output signal coupling. C2 reduces feedback noises and improves signal quality. RV1 is a potentiometer which allows us to adjust output volume or gain. The next slide shows the hardware prototype of our electronic stethoscope. We used a 12-volt DC dual power supply to provide proper operation and full signal swing of IC741. A potentiometer is integrated for real-time gain control, so output can be adjusted according to requirement. This slide shows both the hardware and the output waveform observed on the oscilloscope. The waveform confirms that the input signal was successfully amplified and processed by the circuit. The output indicated that our electronic stethoscope is functioning properly.
For our project, let's take a look at the circuit schematic for our electronic stethoscope. The goal here is to capture a very faint acoustic heartbeat signal, filter out the background noise, and amplify it clearly. The core amplifier. We utilized an IC741 operational amplifier set up in an inverting configuration. We chose this specific setup because it provides excellent stability and allows us to easily control the high gain required to make the heartbeat audible. Filtering out noise. Because the human body and environment introduce a lot of high frequency noise, we integrated an active low pass filter. This is achieved using capacitor C2 of 120 nanofarad working alongside resistor R3. Together they suppress unwanted high frequencies, ensuring we only focus on the low frequency thumbs of the heart. Isolating the heart sound. Additionally, we have DC blocking capacitors C1 and C5 placed at the input and output stages. These act as high-pass filters to block any static DC offsets or drift, ensuring that only the alternating AC signals, the actual heart sound waves, pass through the circuit.
We'll be looking towards the working principle of our system. It uses four main stages. The first stage is the sensing stage, which uses an electron microphone to capture the chest vibrations and convert them into electrical signals. Next is the amplification stage, which has an IC741 to boost the signal to 1000 volts, and then a capacitor filters out the high frequency noise. The third stage is the control stage, where a potentiometer lets us to adjust the volume to a comfortable level. And finally, the output stage uses the coupling capacitor to block the DC components, safely delivering the clean audio to the hearer. Next is the voltage gain calculation. To understand the amplification, we calculate the voltage gain of our inverting amplifier. By taking the ratio of the feedback resistor to the input resistor, we achieved a gain of 1000, which equals 60 decibels. The massive boost is absolutely necessary to lift the tiny microvolt signal of the microphone to the signal that we can actually hear. Now comes the DC bias and voltage gain analysis. We have seen there are certain parameters: bias compensation, midband gain, gain divider factor, and maximum gain system gain. So first of all, the bias compensation uses the resistors R2, which is equal to the parallel of R1 and R3, and which is almost equal to R1. It is 1.2 kilo ohm. The midband gain is actually 1000, as we have discussed earlier, which is equal 60 decibels. The gain divider is about 1 by 11, which means the maximum gain system will be 11,000, which is 80.8 decibels. After that, to keep the audio screen, we have used specific filters. The low pass filters and the high pass filters are used for this purpose. The low pass filter has a cutoff frequency of 1.11 Hz, which actually suppresses the high frequency acoustic noise. And on the other hand, our high pass filter sets a low cutoff at 0.34 Hz at the output stage, which successfully blocks the unwanted DC components and stabilizes the output sound. All these things were necessary. For example, the low pass filter was necessary for us as it blocks high frequencies and only lets the low frequencies to pass through. Therefore, hard sounds like the sound we have of lub dub and the lung sounds are low frequency signals, typically between 20 Hz to 500 Hz. Therefore, it acts as an acoustic noise suppressor. It cuts out the high pitched environmental noises from the stethoscope rubbing against the skin or clothing and the internal electronical circuit hiss, which we call actually. And then the high pass filter is also necessary because it blocks the low frequencies and allows the high frequencies to pass through. It is explicitly used for the DC blocking. When an amplifier boosts the signal up to 1000-fold, any tiny 0 volt to 5 volt DC offset from the electronics gets the amplified too. If that raw DC voltage reaches our ears, it will cause a massive distort, or the audio will be potentially damaging to the ears. Therefore, it filters out the low-frequency baseline wanders caused by the patient's breathing or moving around, keeping the audio signal perfectly centered and stable.
In conclusion, our project successfully designed and implemented a high-gain electronic stethoscope using IC741 operation amplifier. The system was able to amplify weak acoustic signals effectively. Our circuit achieved approximately 1000 times signal amplification while maintaining signal clarity. Noise reduction was improved using a 120 nanofarad capacitor in the feedback path. Overall, the project demonstrated that electronic amplification can improve sound detection performance.